Life is too short to work at a crappy company. That's why Software Engineering Daily is proud to be sponsored by Hired.com, the job marketplace for software engineers. If you accept a job through Hired, they will give you a $2,000 bonus. But as an extra bonus to our listeners, you can get an additional $2,000. That's $4,000 total if you sign up by going to softwareengineeringdaily.com and using the link on the right side of the page to sign up. Hired.com will set you up with 5 great companies for interviews. These are companies like Stripe, Facebook, Uber, companies you would actually want to work for, where you can go and learn the cutting edge of software engineering. Go to softwareengineeringdaily.com, click on the banner on the right, and try out Hired.com. Greg Corrado is a senior research scientist at Google working on artificial intelligence and scalable machine learning, and he's also the co-founder of the Google Brain Project. Greg, welcome to Software Engineering Daily.
Great, I'm really excited to be here.
Google uses machine learning in most of its products, and I want to start by talking about one specific product. Smart Reply is a deep neural network that writes email. From the end user's point of view, how does Smart Reply work?
So the Smart Reply product really targets users that are on the go and are receiving emails on their mobile device, but just want to dash off a quick reply. But using keyboards on mobile devices is often annoying, I find. And so the idea of the system is that what it tries to do is detect when an incoming email on mobile deserves a short response, and then tries to compose a few candidate short responses for you to quickly tap on, maybe edit a little bit, and then send.
And there's been a lot of research about how to understand natural language and then generate natural language based on that understanding. And Smart Reply fits right into this type of problem. So some Google researchers developed an approach called sequence-to-sequence learning at some point before the Smart Reply problem developed. Why is sequence-to-sequence learning a useful approach to building the Smart Reply email system?
Yeah, so sequence-to-sequence learning it's an extraordinarily general approach to machine learning where we don't have to understand or manually specify very much about the format of the input or the structure of the input or the format or structure of the output. So all that we do is we assume that the input is a sequence of events or tokens. It's a string of some sort. And the output is also a sequence or a string of some type. And so what we try to do is we try to learn a general function for mapping one set of strings into another set of strings. And so we initially applied this in the area of machine translation, where we tried to directly learn a translation system, for example, from English to French, just by using machine learning, a machine learning system exposed to pairs of English and French sentences. The way that this fits into Smart Reply is that we can take that same approach because it's so general and so generic and apply it to the problem of generating email responses simply by training a system to predict likely responses to an arbitrary incoming message.
And there's a great blog post about Smart Reply that I will put in the show notes. It goes into how sequence-to-sequence learning is applied. But now that we kind of have a prototypical example of why machine learning would be used at Google, I'd like to shift to talking about the tools and development processes that you use at Google to make machine learning easier. So when you were developing Smart Reply, it was a hypothetical product that was at the intersection of research and software engineering. It was a matter of research because you weren't sure if this was actually going to be a possible product to build. And it would require a very strong understanding of the theory to be able to reason through this problem. But it was also a matter of software engineering because the only way to figure out if it would actually work was by hacking it together and experimenting and implementing some of whatever came out of the research. So there are many people listening who might want to bring more of an ethos of research and engineering to their own workplace. How can teams blend research and engineering in order to make better products?
So the Google approach to blending research and engineering is something that I've really enjoyed and I think is very successful. And part of what you do is you try to cultivate a culture of mutual respect between people who do hard-nosed engineering and people who do really out there research. And by having people who have a research background and some engineering skills, and people who have engineering skills and some interest in pure science, sitting together and working together and trying to build things that they both find exciting and they both sort of respect the skills of their collaborators in developing these products. I really think that that's kind of the essential ingredient. It's almost impossible to find people who are best in class engineers and best in class researchers. If you do find such people, of course you should keep them. But in practice, it's actually better it's more scalable to try to find people who work well together, who see the other party as a natural complement to their skill set.
Right. And what are the most important frameworks and pieces of infrastructure that you can talk about that would help you design a solution for a problem like Smart Reply? And maybe some of these frameworks and infrastructure fit into the point you just made about enabling engineers and researchers to work together.
Yeah. So the Smart Reply system, we actually use the TensorFlow open source package that Google just released in the development of that product, and that's also what serves live traffic is the TensorFlow backend. And we TensorFlow is actually our second generation machine learning toolkit on the Google Brain team. The first toolkit that we developed was called DistBelief, and that was our initial experimental stab at a scalable deep learning system. And it worked quite well, but we learned a lot in the process of building that first system. And we decided to take an entirely fresh start and re-engineer and redesign our library from scratch in a way that was much easier to use, but still retained this great property of being usable both by researchers, and then if it actually works, it's hardened for production. So you can immediately launch it in real products without having to re-implement systems. That's one thing that I think slows a lot of work down elsewhere. If you have a researcher work on their own to develop research code to test an idea, and then the idea seems promising, when you actually want to test it in production, you end up having to rewrite things because research code is not up to production standards. And TensorFlow allows us to use one set of tools both to develop research ideas and to actually launch things in real products.
Right. And we've done some other shows that have touched on this type of problem of translating the models between machine learning engineers and the software engineers that are using their models. If listeners are curious, they can listen to the episode about Y-Hat that I'll put in the show notes. But we should talk about TensorFlow and Disbelief, and I'm really curious about these. So, as you said, Google's early work in machine learning prior to TensorFlow was around a system called DistBelief. How did the DistBelief project shape TensorFlow, the experiences and the lessons from DistBelief?
Yeah, so Disbelief was really targeted very specifically at building very large deep neural networks. So the project started initially as a collaboration between Google X and Google Research and Andrew Ng from Stanford. And when we started out with this idea, Jeff Dean and Andrew Ng were very excited about the idea of building very large neural networks and using Google's infrastructure to train them at speed. And so the original Disbelief system was very tightly coupled to Google's internal infrastructure. And it had really great scalability properties for training very large neural networks. But because it was sort of experimental, we didn't think very much about usability and flexibility. So in constructing TensorFlow, we still wanted to retain all of the good things that we saw in Disbelief about scalability, about it being production hardened, about it being able to handle very large neural networks. But we actually wanted to expand the scope and make something that worked not just for deep learning and neural networks, but that was more general and that you could build other machine learning algorithms on top of. And something that was much easier to learn. The original Disbelief system was very, very difficult to learn. It had a lot of sharp edges. There were a lot of pieces of that abstraction that were not really well designed, and it wouldn't have been the kind of thing that we could have even plausibly open sourced because it was so close to the underlying Google fabric in our data centers. Whereas TensorFlow introduced the appropriate levels of abstraction to say, hey, you can run this on your Linux desktop, or you can run this on your own GPU card, or you can run this on your Android phone or your iOS phone, and you don't need any of Google's infrastructure to do that.
Let's break down the name TensorFlow. What is a tensor?
So a tensor is, I'll start with the formal definition. It's an n-dimensional data array. So what do I mean by that? So a two-dimensional data array is like, for example, a traditional matrix where it has rows and columns, and in each cell you have a datum of a certain type. So maybe you have a floating point matrix that has rows and columns of floating point numbers. That would be called a two-tensor because it's two-dimensional. A one-tensor would be just a vector, just a list of numbers. A zero-tensor would be just a single scalar, just a single number. But a three-tensor, right, that's actually a stack of matrices. It's a three-dimensional cube of numbers. But then what's a four-tensor, right? It's a four-dimensional cube of numbers. So the point of building something with tensors is that in machine learning, we are often dealing with n-dimensional arrays of data that are sets of matrices or other data objects. And we wanted to build something that worked flexibly in these kinds of n-dimensional array spaces really easily, like the way that if you've ever used MATLAB works really well for matrices, which are two-dimensional objects, but it also works very well for n-dimensional objects.
So you've broken down tensor, and flow refers to data flow. What is data flow?
Yeah, so data flow computation is a way of conceptualizing numerical operations. This isn't a new idea. This is something that's been around in the computer science literature for quite a while. But the idea is that you think of your calculation as a graph, where the nodes in the graph, the boxes in your box diagram, the nodes in your graph are mathematical objects or operations, and then the edges, the lines that connect these things, the edges that connect your nodes are places where data are communicated between mathematical operations. So we use this sort of data flow computation model in order to perform and express the computation that's going to be accomplished. So, for example, if we want to multiply a vector and a matrix, we might have an operator that connects these two inputs, that takes two inputs, one that's a vector and one that's a matrix, and then outputs a tensor that's their product.
So, as you said, the model of computation of being a directed acyclic graph it sounds like other streaming frameworks that we've covered on Software Engineering Daily. Like we've covered Spark and Storm and some other frameworks. How does a machine learning framework, or TensorFlow specifically, how does it differ from a streaming framework that is more generalized like Spark or Storm?
Yeah, so the framework that we've built is really something that is targeted at machine learning, where the common case is that you have some sources and sinks of data that are more like the traditional things that you're used to. Like, for example, let's say that we're trying to train a system to do spam prediction. We're still going to have a source that, for example, pulls features about an email and pulls labels about whether or not they were classified, streams them through the graph, and then dumps out answers at the other end. That part is still conserved, but we've made this a stateful system so that, for example, if we're trying to learn the parameters of, let's say, a logistic regression model to do our spam classification, there are special nodes in the graph that are able to both read from and also make updates to or assignments to variables that the user has defined. And these variables can be shared across multiple instances of the same graph and referenced at multiple places within the same graph. And that's really helpful for driving this kind of machine learning approach. And is a big part of what we think makes our system useful.
So TensorFlow can be used on systems that are as small as a mobile phone or as big as a large-scale distributed system. I thought that machine learning was something that was like exclusively a server-side activity. Like I often hear that the phone is just this dumb, lightweight interface into a smart cloud. Why would I want to do machine learning on my phone?
So that's a great question. The current paradigm is to say, well, we need a lot of computational resources and a lot of data to actually perform the learning, to train the model. And so right now that's happening on servers, right? Those are the places, where there's a lot of data and there's a lot of compute resources. But then once you've trained the model on the servers, now you have a choice about where you're going to deploy it. And you can deploy it on the server side and have some client make a connection in order to get its machine learning predictions. And that is the way a lot of systems work. But for latency or privacy reasons, if you can deploy your machine learning system on the device after it's already trained, having a system that makes that possible is actually really an exciting opportunity that is something that I think is just picking up speed now. I think that as things move forward and phones become more powerful and battery life is less of a difficult issue, you'll see more cases of there being on-device learning, not just on-device prediction, but on-device learning as well. And the nice thing about TensorFlow is that you'll be able to survive all of these transitions, right? So if you're doing something today that is both server-side for learning and prediction, and then eventually you want to move prediction into the phone but keep training server-side, you can do that. And then if you believe that you can do some fine-tuning or some learning on-device, you can do that as well.
So when you talk about this on-device learning, could you specify this a little more? Like, I guess I'm having trouble understanding if this is like a big algorithm that Google is distributing across a bunch of phones, or is this like something that gets? I guess I know it's not that, because you just said it's the device gets the learning gets done and then it's basically on the phone. So I don't know. Could you clarify this just a little more? How this actually would work in practice?
Yeah, so a good example of the current state of affairs is that in the TensorFlow open source release, we've released an object recognition model that runs on an Android phone. And so what that means is that you can load up an app that uses this machine learning system in order to recognize objects that are just presented in front of the camera. It's not great. It's actually kind of cute, the sorts of mistakes that it makes, but it is something it's a machine learned object recognition system. Now that system was trained on servers, right? It's not going to be trained on your phone. That would both take a long time and would take an obscene amount of data and an obscene amount of power. So it was trained, in Google data centers to do its task, and then is just being run on the phone locally for latency and also for network bandwidth issues. I do think that there's a possible future where someone will get to the point where what they want to do is they want to, for example, release an app that contains a model that maybe is already pre-trained, but does some additional learning or fine-tuning based on the experience on the device. We actually haven't seen anyone do that just yet that I'm aware of. But I think that that's a possible future.
Okay. So I'd like to take the smart reply example a little further, or maybe if you don't want to talk about that in more specific, we can talk about the image recognition thing. But in any case, I'd like to get a better idea for how one of these things in the abstract translates to actual implementation on top of TensorFlow.
Yeah. So let's talk about the smart reply case. So the way that this sort of thing gets implemented in TensorFlow is that you first have to specify what is the computational graph? What is the structure of the computation that defines your machine learning system? And then you run a training job that basically flows data through this graph and learns the parameters of your machine learning system. And then once you've learned those parameters and you've done some quality testing to give yourself some confidence that the kind of predictions that the system makes are actually the sorts of predictions that you think are good enough quality, then you actually can run it against live traffic. So in the TensorFlow case, in the smart reply case, we decided to take a sequence-to-sequence learning approach. And so what there's a little bit of Python code that constructs the TensorFlow graph for the sequence-to-sequence model. And then there's another little bit of code that pushes a whole bunch of data through that graph and learns the parameters of the graph. And then the graph configuration and the graph's parameters get saved out. And then what we do in our data centers is we load up that same model from those same files, and then that gets served against, it gets run against real traffic that comes through the Gmail servers. For sequence-to-sequence modeling, the graph that defines a sequence-to-sequence model is actually a pretty complicated object. It's the kind of recurrent neural network that we use for sequence-to-sequence model is called an LSTM, or a long short-term memory network. And you actually have to be a little bit of a pre-existing neural networks geek in order to have been familiar with this thing. In the TensorFlow open source release, in the tutorials, we actually give an example of Python code that constructs an LSTM for a machine translation model and trains it against a publicly available data set to, for example, to predict French sentences from English sentences. And then we run it through a little scoring example so that you can see how well it's done. And that's the kind of thing that you would do if you were actually trying to build this whole process out.
Over Thanksgiving, I had a great idea for a web app. So instead of spending time with my family, I locked myself in a room and I started building this application using Express.js because I love full-stack JavaScript. So I was testing my application locally and I was making great progress. So I decided to deploy it and share it with some of my friends and get some feedback. I used DigitalOcean. I signed up for an account using promo code SEDaily, and in 15 minutes, I had my app deployed to a server and running. It was that simple. This was really the first time I had used DigitalOcean. So if you're like me and you like building stuff and you have ideas for projects, give DigitalOcean a shot. It is the fastest and simplest way to deploy an application that I've ever used. If you want to give it a try, go to DigitalOcean.com and use the promo code SEDaily to get $10 in free credits. Check it out. So is a goal of TensorFlow to elevate machine learning to the level of usability where the programmer wouldn't have to know what an LSTM is, wouldn't have to know what maybe even statistical regression, or is that not what TensorFlow is?
Yeah, right now it's not really targeted at people who don't either know or want to learn about machine learning. It's not that turnkey. Instead, It's really targeted at people who either know machine learning and want a handy way of implementing and scaling algorithms that they're already familiar with, or people who are learning machine learning and want to start out learning it in a software framework that is going to be around and is sort of has some industrial legs to it.
Right. Okay.
So I think that most of the time, the core TensorFlow open source library allows you to get down into the details if you want. You really can see every matrix multiplication and matrix addition in the entire machine learning algorithm if you want to. But we try to provide some libraries that are slightly higher level that show you how you might, for example, build these networks of computation using the Python interface. And we also provide some visualization tools that we think are really important. That this is called TensorBoard in the open source release. And what it allows you to do, for example, is it actually gives you a pictorial representation of your graph where you see nodes and edges of this thing that you built that you're running data through, so that you're not just flying blind, right? So that you have the chance to, okay, I'm going to build this graph, I'm going to run it, I'm going to make this change, and I can see a change in the diagram, and then I can see how that affects computation.
Yeah, that sounds like a super useful feature. So at each node, to make this more concrete for listeners, at each node in a TensorFlow graph, an operation is taking place. And the implementation of that operation differs depending on the type of device that is running the TensorFlow computation. So for a matrix multiplication, there might be a different implementation for an operation depending on if it's on a GPU or on a CPU. And the layer of abstraction that represents these different device-specific implementations is called the kernel. So why is this necessary? Why do we need different operational implementations for different devices?
Yeah, so this is a great question. So this is part of the power of thinking about our computation as a graph, right? We know that matrix multiplication is a very well-defined mathematical operation. We know how it should work, and the user who's trying to express something about the computation that they want to execute only needs to know that they want to perform a matrix multiplication. But we want to have different implementations of that, different kernels for different kinds of hardware devices in order to have portability without sacrificing performance. So what you're able to do in the TensorFlow graph is either automatically or manually. Every node in the graph needs to be assigned to some device that's able to do the computation. You could, for example, assign them all to the CPU in your desktop. And then we would use the C++ implementation of matrix multiplication and vector addition and all of these other operators that are in your graph. And there are actually a lot of operators that we provide implementations for. But if you're using the CPU, you're going to get good performance, but you'll for some of these operations, you can get better performance if you happen to have a high performance GPU in your desktop. And so when you want to map that, when you instead want to place the computation for this node on the GPU instead of the CPU, you're going to need a different implementation to take advantage of the computational structure of the GPU. Similarly, on the phone, you don't have the same matrix libraries available. The CPU characteristics are very different. If you have a GPU on your phone, those characteristics are also very different. And so the kernels give us the ability to abstract the details of the hardware away. And if somebody comes up with, if there's new hardware or new functionality that comes out, we can support that really easily in TensorFlow just by adding new kernels that are new implementations without having the machine learning person rewrite their code in order to support this new kind of computation.
That's great. So in the simplest execution scenario, TensorFlow is executing on a single device, like you defined in the example of the mobile phone running the image recognition machine learning model. But more typically, TensorFlow is executing across multiple devices, and distributed machine learning, like any distributed systems problem, can lead to some difficult complications. What are the complications that take place in distributed machine learning?
Yeah, so distributed machine learning is it's the same kind of conceptual leap as a programmer that we all had to make when we went from single-threaded programming to concurrent programming. There are just a lot of pitfalls. There are things that can make your computation suddenly incorrect, like a race condition. And there are also a bunch of things that you can do that can impact performance negatively. And so distributed machine learning is actually hard. The simplest thing that we can do is what we usually describe as model parallelism, where what we do is we have a big machine learning model, like we have a lot of nodes in our graph, and we want to stream data through that graph very efficiently. What we can do is we can assign different subsets of nodes to different devices and basically pipeline computation throughout the entire graph. So, for example, if you have multiple CPUs on your device, you might assign different nodes to different CPUs. If you have some CPUs and GPUs, there might be some operations that do well on one part or the other, and you're kind of streaming the computation through, usually within one box, but you could in principle do this across multiple boxes. And so what TensorFlow does to make that easy is that when you move data between devices, there's all kinds of copying and handshaking that needs to be done, and needs to be done efficiently. But you don't want to add unnecessary complexity if you don't need to. And we try to keep all of that under the covers for TensorFlow so that it performs very well. And we do our very best to hide all of that.
So as you mentioned, the fault tolerance and stuff is hidden beneath the covers, but I'd like to peek under those covers and get an idea of how TensorFlow supports failures and errors. Like if a machine fails, I don't know, give me an example of how like a Byzantine fault would be handled in TensorFlow.
Yeah, so an important kind of fault tolerance comes up in the truly distributed computational setting where we have where we're actually executing the same graph on different slices of data concurrently. This is something that's not in the current open source release, but is in our next release. And the kind of failure mode that you can have is, let's imagine that you're doing distributed computation. You have, say, 100 replicas of the computation, each working on a different subset of your data, and one of those machines goes down and fails. what you don't want to do is you don't want to have your entire machine learning pipeline halt while that one worker restarts and re-gets the parameters and figures out where its data are and starts going again. So it's very important in these kinds of distributed computational settings to have these kinds of failures be very graceful in the sense that they very rarely cause the system to halt entirely. You don't mind if failures slow things down, but it's very important that failures not stop forward progress. And this is the kind of thing that we spend a lot of time and engineering effort getting right in TensorFlow so that we can train really big models and use lots of resources without pausing every time we lose a resource.
So liveness is not an option.
Right, exactly.
Okay, very interesting. So a client will sometimes want to execute just a subgraph of the entire execution graph. And this was kind of confusing for me because I thought that an execution graph represented all of the operations of a machine learning job. Like, why would a client want to execute only part of a graph?
So that's a great question. So we built this in right from the beginning. There are other Dataflow pipelines where you build a graph and then you either execute all of the graph or none of the graph, right? It's a wholesale process. But in practice, we find that it's actually really, really helpful to be able to execute different subsets of the graph at different times. So a really simple but very strongly motivating case is, let's say you build this whole graph and then you want to debug it, right? So you build the whole graph, you decide that you want all of the nodes assigned to the GPU initially, but you want to debug some subgraph. You want to see what the inputs and outputs are to some part of your computation. You really want to be able to peek and poke at tensors anywhere in your graph in order to be able to understand the computation and debug it. And in order to do that, that really amounts to executing subgraphs. So debugging, I think, would have been a sufficient motivation, but in fact, there are other really good reasons. Another really good reason is that often you construct a big graph. The graph for training is always larger than the graph for execution or inference, as we call it. So when you're serving a larger piece of traffic, you don't need to compute the gradients and update the variables and all of that sort of stuff. You just need to get to your prediction. And so it's actually pretty common to, for example, if you want to do online evaluation of how your model is doing against test data, you would actually only want to run it as far as making its prediction. You don't want it to update its parameters. You don't want to compute any gradients. And so in that case, you're also obviously only wanting to run a subgraph without having to construct a parallel graph that is the logical subset.
Okay, interesting. So, we already talked a little bit about distributed systems, but I have another question. The distributed nodes of the graph, they're across all these different machines, and they need to communicate with each other in order to complete the machine learning job. Can you talk a little bit about the layer of communication?
Yeah, so the communication layer is very, very important, and this is something else that TensorFlow will abstract for us. So, within Google, there are many communication protocols that operate between devices, for example, that are on a network. Some of these protocols are public. There are some protocols that are internal to Google only. And part of what we want to do in TensorFlow is we're going to abstract away all of these communication protocols. We know which protocols we're using internally for distributed computation, but for the upcoming open source release where we do distributed computation externally, we're going to support a variety of interfaces and abstractions, but we don't have the details on that just yet.
Okay. Well, speaking of things you can talk about, though, TensorFlow is being open sourced, and one of the big motivations for open sourcing stuff is always that you get more eyes on it, you get more contributors. What are the things that you would like to see the open source community dive into in TensorFlow and fix and improve?
Yeah, so that's a great question. So the one great area is language support. So there's the phase of graph computation, specifying what the computational graph would be. And there's also a phase of graph execution, where you're actually running data through the graph. We've provided Python and C++ interfaces to both of these aspects of the process. But there are a lot of other languages out there, and we chose Python and C++ because those are the languages that we use most. But in principle, there are a host of other front-end languages that could be used, and we've tried to make this easy for the open source community by making a swiggable interface. But I think people contributing an interface for their favorite language would be really, really helpful, as well as looking at, if someone wants to dive into more details, looking at operators for improved efficiency or missing mathematical operators where you're like, oh, well, actually, this matrix decomposition operator would be really helpful, and so on and so forth.
Okay, well, that's great. It was really great talking to you, Greg Corrado, and I'm a huge fan of TensorFlow. If you guys ever have anything else to discuss, you consider it a standing invitation to come back on Software Engineering Daily.
Thanks so much. This has really been a pleasure. And I hope people like it.